All right, so what's good, class? I'm back, and before we start today's lecture over simple harmonic motion, I want to play a recording that I made for you. It was actually a recording that came about one morning after I made a cup of coffee, and I had heard something that was a little unusual. I guess maybe I had woken up early, earlier than most mornings, and yeah, I was like, wow, this will be a great thing to share with the class. So let me play this for you. It's actually an audio recording, um, and I want you to listen to it carefully and, um, appreciate it for what it is, its beauty. So, what you heard in that audio recording, hopefully you were able to hear it. If not, then, I apologize. Maybe I'll share that audio with you. But what you heard in that audio recording was different sounds. There were sounds of birds chirping, which was the sound I was initially intending to record. There was also this alarm going on in the background. It was a bang, bang, bang. And then you would also hear the sounds of cars as they were driving by. So what you were listening to was the hustle and bustle of Austin, Texas. And within that hustle and bustle, I realized all of the periodicity which had been exhibited within this audio, right? Like you can hear the alarm. It's always occurring at a particular frequency. It was dun dun dun. You could hear the birds chirping. They were they weren't necessarily uniform, but you would hear them chirp choo 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 choo. And, me as a physicist, I recognize that you're able to even describe even that pattern using this idea of waves, and this idea of describing the alarm itself and its repeat of its sound is also described using this waves. Actually, the simple harmonic motion doesn't quite completely describe the frequency at which the birds were chirping with. In fact, that will be discussed a little more later in the course when we begin to discuss Fourier. But I just want to say, like, like it's really fascinating that you're able to describe even the sound that you're hearing from the different cars passing by using these ideas that we're discussing. So, I want to continue on into our semester. That's what I'll call this, our semester, or I guess the playlist technically. But for the language, for the lingo of this course, uh, this will be lectures. These are your lectures. Um, so I want to continue on with the description of simple harmonic motion, or SHM for short. All right, I'm only saying that so that I don't have to write it over and over all the time. So if you remember last time, we had a mass M attached to some spring with spring constant K. And whoops, see, I'm still practicing. I'm gonna get better at it, I promise. But we took this mass, remember, and we uh, pulled on it, which ultimately stretched the spring some distance, And this mass was, because it's sitting on this frictionless surface. I didn't specify that last time. I hope that you were able to piece together that this surface was frictionless. But if not, let me allow me to specify that now. This surface is frictionless. Okay, that's the intention here. If this surface were not frictionless, the motion which we're discussing at this moment would not be described by uh, what our guess was. Remember our guess, which was x of t, which was equal to a sine of omega t plus phi naught. That was our guess last time. That's what we said, describe this motion. And actually, I wanted you to show that this was the case. In order to do that, you needed to take a couple of derivatives of this x of t. In fact, you needed to take 2 time derivatives of this x of t and put it into that equation of motion, which we had gotten from using the momentum principle or Newton's second law. You would take that thing and see if it was true. And what you ended up finding, if you were able to follow along or able to complete this task, which I had given you, if you weren't able to complete that task, you should be able to go to Instagram and view the solution. The solution should be posted by the time you're seeing this. Oh, actually, yeah, I guess at the end of the video, I'll continue on to that. But next time I know to at the beginning discuss like, sharing, and subscribing. So actually, let me go ahead and say that now. Like, share, and subscribe. Also, be sure to follow me on Instagram. You can do so by searching Lord LORD underscore Claiborne, CLAIBORNE underscore IG. That's where you can find me. You can also go to Claiborne40acres.com and you'll be able to get more information about me. And hopefully, I'll post these lectures there as well. Maybe I'll post my actual written lecture notes there. But yeah, let's get back to the discussion. So we were discussing confirming that our guess x of t is equal to some constant a sine of omega t plus phi naught satisfied this equation of motion, which we said was m d squared, the second time derivative of x of t, was equal to minus k x of t. Now, if you were able to follow along with this, you would find that this is true, that this can be true. It can be true. It's not always true, but it can be true if omega squared were equal to k over m. So this thing called omega, this constant which we discussed earlier, omega, let me spell that for you, omega. So the question is, what is this omega? What is omega? And we'll discuss a little bit more about what omega is throughout this video. So let's continue on and look at this motion in greater detail. And the way that we'll do this is through a drawing of our function x of t. Okay, that's how we'll do this, through our function x of t. There you go. So here on this axis we'll have t. Over here we'll have x of t. There it goes right there. And then we have we said that x of t, I'll write it again up here. That way we don't forget, a sine of omega t plus phi naught. Now make sure you like, comment, and subscribe. And when you comment, let me know if I'm discussing things too quickly or if I'm moving too slowly. But here we have our a, and here we have some minus a. And so now let's draw what this sine of omega t plus phi naught could possibly look like on this curve. What does this curve look like? Well, it's just a simple sine wave. It goes like this. Oops. You can see here, my intention here is to have this thing bounded by a and minus a. Okay, and so uh, the first thing that I will note here, and actually your question's coming earlier in this video. Uh, what I want you to do is I actually want you to tell me how, or actually determine what the value of the spacing is from here to here. What is the value? What is this? What is this equal to? I'll call it some delta t. What is this delta t? Delta t. What is the value of delta t? What is the value of delta t? Okay, and so I'll let you think about that. But a couple of things that we want to discuss in this wave are a couple of its properties, its characteristics, which it exhibits. Firstly, like I mentioned earlier, this wave, it's bounded between a and minus a. All right, so that function x of t is bounded through here. It doesn't go over it or past it. Secondly, the second thing that you notice is that it actually begins to repeat itself. It repeats itself after some amount of time. That amount of time for which it takes to repeat itself, I'm going to call t the period. Uh, I'll use this color blue. Blue is actually my favorite color. Um, but the amount of time for which it takes to repeat itself is t. This t, oh, maybe I should switch back to black now. All right, so this t is what I'm going to call a period. This is a period. Period, okay? It's gonna, maybe I should do that the other way around. Let's do it like this. So your period, uh, uh, the time it takes for the motion to repeat itself. Uh, yes, it's the time it takes for the motion to repeat itself. I'm going to denote that with some variable t, okay? Just move this a little bit like that. See, this iPad thing is great if you do it, if you use it correctly. T, period T. See that? All right. So see here, it repeats itself, right? And so over here, you see, um, you have, it goes down initially, and then it comes back up, and then eventually it comes back, and then it repeats itself. It does it again. And the amount of time that it takes to do that is what we're calling the period T, okay? Or you can actually even come to here, like let's say at the, let's change this color then to my favorite, blue. All right, see, even here, it starts here at 0, it goes up, comes back down, and it comes back to 0, and then it does it again. It goes up, and it comes back down. And if this were longer, it would actually continue repeating itself. And so the time that it takes from going to here, back to here, that is also a period t, right? So that's what the period is. And remember, we had discussed this periodicity thing. Um, and that's literally what this is. It's the amount of time that it takes to repeat itself. So at the beginning of the recording, I had played that audio for you. So the amount of time that it took for the alarm to set off, to go off, like and that was a period, right? So so it would give you those three bursts, but then the amount of time that it took to repeat that same process. That is its period. That's the period of of that sound. Okay, so maybe I can actually write this out for you a little better. So there were two things that we mentioned here. Um, Two things we mentioned. Important characters of simple harmonic motion, right? So one, it is confined within the limits of its amplitude. And then two, the motion repeats itself after a time t. T, which is called period. Okay, so let's discuss a little bit more about what this period is, right? So after some amount of time t, what we will have realized is that our sine function begins to repeat itself. And when the sine function repeats itself, that means the argument within the sine function, the argument within the sine function has increased by a value of 2 pi, right? These sine functions, you may be familiar, you should be familiar, but in case you aren't, you could think of, um, I'd like for you to think of this idea of a unit circle, right? This would be like some x and some y, and then you'd have some circle. This is actually a little off script, but that's okay. Sometimes you have to adjust and think on your feet, right? But in case you aren't familiar with what I'm trying to suggest, what I'm saying to you is that so sine would actually begin up here, right? Uh, the circle has 2 pi radians, right? So once you go over a full circle, you will have uh, officially gone 2 pi radians or 360 degrees. And so when a sine function begins to repeat itself, when it repeats itself like this, so it goes from this zero back to this zero, this sine wave has officially, this argument within the sine has increased by a value of 2 pi. Okay, hopefully that's clear. If not, maybe you can ask more questions. But that's the amount. That's the value at which the argument within the sine function has increased in order for the sine function to begin to repeat. It will have increased by a value of 2 pi. And so, uh, if that is the case, that means that x of t plus 2 pi, right, has increased by 2 pi radians. It must be equal to x of t plus our period t, right? Like I said, it will have increased by a value of 2 pi from here to here, right? So 2 pi must also be equal to this thing. So let's see what happens here. If we put in x of t, right? Remember what our x of t is. Man, I'm going to be writing this all day long, aren't I? Sine of omega t plus phi naught. Okay, so what we're going to do is we're going to write it out, right? So we got some a sine of omega t plus phi naught plus 2 pi, right? That's me putting in this t plus 2 pi into the argument of x of t. See, t plus 2 pi, I put t plus 2 pi into our argument for x of t. So right here, I put in t plus 2 pi. Well, okay, maybe I can make it a little clearer because I guess I do kind of skip a step. So for the audience who may not necessarily be able to follow along, I'll make it even abundantly. I'll make it even abundantly more clear. T plus 2 pi plus phi naught. Okay, so I'm putting in t plus 2 pi into the argument of x of t. All right, and that must be equal to a sine of omega, and this is t plus t, right, plus phi naught. These two things have to be equal. Well, we obviously see here, if these two things are equal, if this statement is true, then it must be, obviously these a's cancel because these two things are equal, but it must be the case that these two arguments, that this omega t plus 2 pi plus phi naught must be equal to omega t plus phi naught. All right, the arguments inside our sine function must be equal in order for the value of this function to be the same. All right, that hopefully that's clear. Why is that the case? It's because our sine function is a one-to-one function. All right. Well, I get yes, it's one-to-one. All right. That may be a little mathy. All right. So we don't necessarily have to worry about it. Just know that I'm saying to you it's true. Okay, that the argument inside this sine function must be equal to the argument of the sine function, and in order for this statement to remain true. So let's continue on. If that is the case, that must mean that omega t plus 2 pi plus phi naught has to equal omega t plus phi naught. All right, so in such case, we know that this is true. If this is true, then, well, obviously phi naught on both sides means that that cancels. We'll get, I'll just do the algebra. That way, anyone who does not necessarily know how to do the algebra themselves at the moment can learn it, or at least be exposed to it, and then be able to do it for themselves in the future. In the future, I may, skip this step, but for now, I will actually show it. So it must be that we'll take this omega multiplied by t, omega t plus 2 pi omega. I like to put the numbers 2 and pi in front of omega, has to equal omega t plus omega capital T r period. And so we see that on both sides we have omega t, right? So what are we left with? We're left with something that has gone wrong here. Let's see here. What have I done wrong? This is actually kind of funny. Oh, yes. I see what's going on here. Can you see what happened here? Yes, I see. I see. Yes, okay. All right, I see where I've gone wrong here. So actually, let's take a step back. Here this is actually a good thing to think about. So here, where is it at? Okay, here where I've put t plus 2 pi, I suppose I actually did not mean to put this t plus 2 pi into the argument for t. Actually, what I wanted to do was actually just put t plus 2 pi. So here for t, I didn't want to put t plus 2 pi. In fact, I just wanted to put t and then put plus 2 pi within the argument. So actually, that's my mistake here. So let's go back and correct that. All right. I'm glad that I was able to see this. And this is actually really good because it lets you know that no, you don't always have to be perfect or get it right on the very first try. Sometimes, as you're going through your reasoning, you realize, oh, I actually made a mistake earlier. And so now I can go back and actually fix that. So, this is actually really good. So what I actually meant to put here was this. This is actually what I wanted to put, okay? And so hopefully So you know what? For my mistake, I'll use red, right? So omega t plus 2 pi plus phi naught, all right? So actually here, this was once again another error. So we don't want that there. So we just want omega t plus 2 pi, okay? And so what happens here? We won't get an omega here, all right? Hopefully that's clear. If it is not clear, please ask about it. I will gladly explain or do my best to try to explain exactly what happened there. Okay, so now we see, from here we see that 2 pi must be equal to omega t. And why do we do all this? We've already defined what this thing t, the period was, right? It was the amount of time that it takes for the sine wave to repeat itself. But ultimately, we want to figure out, what is this thing omega? What is this? What is this? Well, we can see here, from here, we see that t, our period, is equal to 2 pi over omega. Or the more relevant thing, which probably could have just uh, um, done from the get-go, we see here that omega is equal to 2 pi over t. So omega, this constant that we were referring to, omega, is equal to 2 pi over t. So it is the frequency at which it takes to for the function to repeat itself, right? Actually, what is the title it's given actually is the angular frequency. So omega is what I'm going to call sorry, actually what I should write is the angular frequency. The angular frequency, omega, all right, is given this value, this constant omega. That's what I'm calling it. And maybe I can write that even better because I don't want there to be any confusion, all right? This isn't necessarily a W, but it is shaped like a W. Ugh, that was badly written. That's all right. Omega. There we go. That's actually probably the most accurate drawing of omega. It's a Greek letter. It's a lowercase omega. You know, you've probably seen the capital omega before, the capital Greek letter omega. Um, but that's what this is. It's a lowercase omega. And it is the angular frequency, or the rate at which the function, I'd say the motion, or uh, the, the function, I'll just say the rate at which it takes to repeat 2 pi, yeah, to increase by 2 pi. The rate at which it takes to increase 2 pi. What it takes to increase 2 pi, it could be the motion, it could be anything. It could be some function to increase by its argument to increase by some value of 2 pi. All right, so that's what this is. That's what this omega is. This, once again, this omega, and this is a very important quantity. That's why I'm like ultimately repeating it so much. It's the rate. See, you see the period. It's the rate at which it takes to go for it to repeat some value 2 pi. So it's like a velocity. It's exactly a velocity. That is what it is. It's a velocity. So here, our circle, right? And if I told you that going around in the circle was, it traveled some distance, some radians of 2 pi, it's the amount of time, or rather, it's the rate at which it takes to repeat at 2 pi. So let's say this took me 1 second to go around, right? So it would be 2 pi divided by 1 second. But let's say it took me 2 seconds, so I went slower. That'd be the angular frequency at which it took to go around 2 pi, or even up here. Uh, the angular frequency is the amount of time that it took me to do that, right? So I hope that, or the rate at which it took me to do that, not the amount of time. This is the amount of time, but it's the rate at which you do that. It's like the velocity, right? It's a time derivative of something. I can say that. Okay, so let's continue. So ultimately, now we know what this constant omega is, but uh, what are the things that we don't know? There's two things we don't know, two remaining unknowns. One of those unknowns is A, the quantity A. What is A? What is A? And then two, we don't know phi naught, our phase factor, right? So this A is the amplitude. We don't know that yet. Just want to remind you what they are, and this phase factor. So the question is, how would you be able to determine what these two quantities are, right? And the way that you would need to do this is by specifying at t equals 0 two things. All right, now, because this is a second order differential equation, that just means that there is two time derivatives in the equations of motion that I showed you earlier, right? It was the d squared x dt squared was equal to kx, well, minus kx. The reason it's a second order differential equation is because you took two time derivatives, right? There's an within the expression, there's two time derivatives. Now that because there's two time derivatives, it means that you need two conditions in order to be able to determine completely, you'll completely determine what the motion of the object will be in time as long as you specify two things, all right? Now, for different types of differential equations, the things that you want to specify may be different. So let's say this were some derivatives in space. You might want to specify the different boundaries. You might want to, if it was a second order differential equation, you would need to specify maybe two positions in space, or maybe you would specify, I don't know, the velocity of something of that nature. Um, or actually, I'm sorry, I misspoke. But okay, I guess I could get mathy. There's two types of conditions. There's Dirichlet boundary conditions, and there's Neumann boundary conditions. But ultimately, I'm saying that when your differential equation is expressed in terms of spatial derivatives, you'll use boundary conditions. But here, these aren't spatial derivatives. These are time derivatives. The function that we're interested in is x of t. It's a time derivative. So instead of boundary conditions, what we're going to use are these things called an initial condition. All right? So let me say at our time at t equals 0, let's say that x of t were equal to, I'm going to call it a with a hat tilde. No. Let's not do that. Actually, we can do it even better. We can do it even better. X naught. Yes. So it's x naught, not as in 0. That's what naught is. No, nothing. And we can also specify another thing, which would be the time derivative of x of t. Or you could also specify. Oh, sorry. Oh yes, I guess I. Oops. Equals 0. At t equals 0. So x at t equals 0 is x naught. And then the second thing that we'll specify is the velocity at t equals 0. So that the velocity t equals 0, we're going to say is v naught. All right. So, I won't spend too much time specifying more about the boundary condition or the initial conditions of which we're specifying, I'll leave that to your differential equations professor. However, if you have more questions about that, please feel free to ask about it in the comments. Maybe a mathematician will get back to you, or if I know the answer or if I'm able to point you in the right direction, I will definitely answer you. All right, so please feel free to ask about these initial conditions. Um, yeah, but ultimately, let's continue on with these two initial conditions. How can we use this information to determine what A and phi naught are, our amplitude and phase factor? Well, we already know that x of t is equal to a sine of omega t plus phi naught. We know that already. That's a given. Um, but now we need to determine what our velocity is. And if you weren't able to answer the question before, maybe this will be even more assistance to you so that you can go back and answer that question from the first lecture. We know that v, our velocity in time, is going to be the time derivative of this thing. So we're going to end up with some a omega cosine omega t plus phi naught. And this is our velocity, all right? Just remember that v of t, let me try and specify this. It's dx dt. I'm specifying this for if you needed that extra hint. Sometimes you need that extra push. Need to specify exactly what I'm referring to, but this is exactly what I'm saying. I'm saying that v of t is dx dt, and so I took a time derivative of this x of our guess, remember? Okay, so now we need to apply our initial condition. So we're going to take x of t equals 0. We're going to plug in 0 here. And we know that's equal to x naught. We said it was x naught. So it's x naught is equal to a and sine of omega times 0. So omega times 0 is 0. So we're going to get sine of phi naught. And then we're going to do the same for v. We're going to get our v, t equals 0, is equal to v naught, which is equal to a omega cosine of phi naught. All right, and so now I'm going to label them. I'm going to label this one 1, and I'll label this one as 2. All right, and so ultimately, you know what? This is something that I want you to do for yourself. I want you to determine. This is a good question, actually. This is a great question, which I think you should be able to do if you were able to follow along, or kind of follow along. I want you to determine what A is given 1 and 2. All right, so you should be able to determine what A is using 1 and 2. There's a little strategy that you can use to do this. I'll make a video on how to continue on and do that, but um, as your assignment for the time being, I want you, in this video, you have 2 so far. The first is determining the value of delta t, right? How do you find what delta t is? And then secondly, I'm not going to give you a hint for that. And then secondly, I want you to determine what the value of A is given 1 and 2, all right? So that's what I want you to go on and do. Okay, and then secondly, I'll actually solve for phi naught myself. So to solve for phi naught, you divide 1 by 2. All right, when you do that, you get x naught divided by v naught. What is that equal to? Well, actually, I'll write it out for you. So x naught divided by v naught. The a's cancel, right? You get this 1 over omega. You get sine of phi naught divided by cosine of phi naught. And that's equal to 1 over omega tan phi naught, right? Because sine over cosine is tangent. So that's what you'll get there. LOL, I think someone's about to interrupt me. Hopefully they won't. But if they do, that's okay. Yes, they will. Yo, what's up? Yeah, come on. Yeah. No, I'm not in a meeting. I'm just recording a video, actually. So now look, you get to see my office mate. There you go.
And oh, that's your the lecture stuff.
Yeah, that's exactly what it is. So you get to be in the video. So I'm posting it on YouTube. So just letting you know. Yeah, okay. He's in the video. All right. So yeah. Okay. So let me continue. So we're solving for phi naught. So what do we do now? So we have our x naught divided by v naught. We multiply this omega, right? Both sides by omega. And that's equal to tangent v naught. And now all you have to do is take the inverse tan, and you will have what phi naught is. All right, so phi naught, whoops, that was badly written. Phi naught is equal to tangent inverse of x naught omega divided by v naught. All right, and that's what you end up finding phi naught to be, our phase factor. All right. So lastly, I want to specify something that I'm actually not very familiar with myself. So I want to pose this question to someone who may be a little more experienced in within physics, because this is a physics question. This isn't necessarily a math question, but this math question, but the math of this statement that I've written here, that phi naught is tan inverse of x naught omega over phi naught, this mathematically does not necessarily match physically what is capable of occurring, right? Remember I told you that we can begin our measurements. We can begin our measurements in the position of our mass at any time we like, right? And that's going to result in the value of this phi naught. So I could wait, like let's say I started here and I waited till here. That would have been some pi over 2 amount of time, right? But I could also start my recording here, or I could start my recording here, or I could start my recording here until, well, actually here. And you know, it's ultimately up until this value of 2 pi. So the question then becomes, this tangent inverse here. This function states that phi naught can only take values between minus pi over 2 and pi over 2. Right? That's what tan inverse looks like. Tan inverse, see, it's over here. It's some minus pi over 2 and some pi over 2. Right? And it looks like this. It goes like this. Right? So let's say this was tan minus x, right? So that's what this is. That's what this says. That phi naught can only take values from minus pi over 2 to pi over 2. But like I just told you, physically, in the real world, in real life, right? I can make measurements at any time I like. It doesn't even have to be at 2 pi. It could be at, 4 pi, somewhere out here. So can someone please explain to me how do you accurately describe this? Like, why is this the case? Why are we bound mathematically by this, but physically you don't necessarily have to be? And like I said, that's a physics question. That's not a math question. That's a physics question. That's a question that is based on your development of your knowledge, your intuition for exactly what's happening here. So in the comments, please, if you're a little more experienced than I am, I'd love for you to answer that question for me. Thank you. Okay, so let's continue. So, this is the last thing I want to state here. So, we had that guess initially that guess. So our initial guess was that x of t was equal to some a sine of omega t plus phi naught, right? But this function here, this guess, this is a function that exists for all times, right? But we knew that before t equals 0, let's say that let's suggest or let's say that before we pulled the mass, right? Before we pulled the block with mass m and spring constant k, before we pulled this thing, this would not accurately describe the motion of this mass at all, right? So the thing is, you need to be able to describe like the actual physical content. This is once again more physics. We want a more accurate description of exactly what it is that describes the motion of the behavior of this mass for all times, not just give some statement that is in general true and it exists for all time. Okay, like in this situation, we wanted to be able to describe every situation. Like in this situation, before we pulled on the mass, this mass is just sitting here. It's not moving. It's in its position that initially was labeled x equals 0. Right? So now we want to be able to describe even the situation before we pull the mass and it begins its oscillation back and forth. And we also want to be able to describe at a later time and when we stop it. Let's call it t stop. We decided that after some time, so let's say before t equals 0, it had no motion, right? Dang, if it had no motion, that's bad, right? Slow motion is better than no motion, but I mean, geez. But no, so I'm just joking. Anyways, uh, so then, like at t equals 0, we pulled on it, right? We pulled on the mass. T equals 0, we pulled it to some position, which, well, what did we say? We said this is x equals 0. This was x naught, right? And then at some later time, let's say at some later time, we stopped it again over here at x equals 0. We stopped it. So I don't know, I'll call it some t stop. We want to be able to accurately describe all three of these situations, right? And in order to do, right? Because when we look at this, our initial guess, this doesn't describe uh, t less than 0. This also doesn't describe when we reach t stop, right? It's our sine function. Our sine function only describes after we let this thing go. So it only describes t greater than and equal to 0. This thing only describes t greater than and equal to 0. So this is, so our a, I said, I'll write it like this actually. So for t less than 0, we don't know what to have right there. But for t less than, well, greater than and equal to 0, greater than equal to 0, and it's actually less than equal to t stop, right? Do we have a description of the situation? X of t is equal to a sine of omega t plus phi naught. That, yes, it describes this situation perfectly, but it doesn't describe a t as less than 0. So what do we need? Actually, we need to add something. X of t is equal to 0, right? So for t less than 0, x of t is equal to 0, right? It's sitting here at the position x equals 0. And for t greater than or equal to t stop, maybe, and actually this shouldn't even be equal to, this is just less than. But for t equals to t greater than or equal to t stop, we once again need to specify the motion, which x of t is equal to, once again, 0. We stopped it at x equals 0. So what we ultimately needed to do to be able to describe the full situation, and this is like actually very important, all right? You have to remember, ultimately, what are we doing? Right? We are making these mathematical constructs or using these mathematical constructs as tools. They're kind of a way to describe what's happening. But we also have to remember the limitations in which they actually accurately depict what it is that we're trying to describe. And so ultimately, what we needed to do in order to describe the motion of our block for times less than 0, the time after we pulled it and let it go, and the time after we stopped it, we needed to actually add two more descriptions of it, okay? And so ultimately, this is what I like to call a piecewise description. Um, and I'm out of space over here. See, once again, this is a great argument for this iPad method because that's all it took for me. A piecewise description. All right, so don't forget that you also have to include uh, this type of description to be able to accurately uh, describe any motion in time, right? We have to remember that the math doesn't necessarily um, always um, relay exactly what it is that we're trying to describe without being very specific. We have to be very specific about what we're trying to say. Okay, and so we needed to add those two extra descriptions in order to accurately depict uh, the mass before we stretched it on the spring, the mass after we let it go, and what it would do, its behavior, and then also after we stopped it. Okay, so um, I hope that's clear. If that was not clear, please in the comments, uh, I'd love for you to, let me know what it is I could have described better, or what it is that you didn't understand. But ultimately, um, that is everything for today's lecture. And so, I want to say thank you for your time, and class is dismissed. All right. Remember, like, comment, and subscribe. All right. See you next time.